Hi, my name is Diogo and I'll be presenting the work titled An Extension for Transactional Memory in OpenMP. Here's a summary of this presentation. Introduction. Transactional memory, or TM, provides a high-level concurrency control abstraction, and some of the benefits of using TM over locked-based systems are composability, scalability, robustness, and productivity. There are three main implementations of TM: software, hardware, and hybrid. We focus specifically on software. Modern APIs like OpenMP, TBB, and recent standards in C++ do not include a native TM module. When using transactional memory, a programmer defines transactions by placing a set of language instructions to create an atomic block. This block represents a critical section and should only contain statements with reversible effects. A runtime system allows threads to execute atomic blocks concurrently, making it appear as if only one thread is executing at a time. There are different mechanisms of data sharing between tasks in the same parallel region. However, there's a gap that can be covered by the adoption of TM support. This gap must be seen as a third-party library or extension of expression power, but not a totally foreign resource. TM is usually introduced through extensions. In OpenMP, this is presented as an interface that handles transactions via the introduction of new specific directives. The OpenMP, or Open Multiprocessing Specification, defines an API to explore concurrency in C, C++, and Fortran programs. This specification is a multi-threaded programming tool with high degree of portability. OpenMP focuses on shared memory environments. Its API includes the specification of environments variables, service library, and a set of directives. The indication of concurrent sections in the code is carried out explicitly via annotations in the code that includes directives and clauses. Directives are used as the basic elements to describe the concurrency of a program and synchronization points. A directive is made of one or more commands, which may be followed by clauses. Directives are used in a parallel region and have the form of this notation: pragma OMP with a list of directives and a list of clauses. The notation pragma OMP instructs the preprocessor that an OpenMP directive will be expanded so that its corresponding code is generated. OpenMP directives supports several clauses. These clauses are optional, but provide a simple and powerful way to control the behavior of its constructor. In practice, some clauses are almost indispensable. Clauses can include the syntax required to specify which variables are shared and which are private for each task. It is necessary to coordinate access by multiple threads and in order to ensure correctness. This is made using the available synchronization mechanisms and tasks parameterization clauses. Now for the proposal of this work. The main objective is to propose an extension to OpenMP interface and introducing resources to handle transactional memory, and to associate the semantics of operations on transactional memory with those offered by other operations already available in OpenMP. Some of the motivations include the introduction of TM mechanisms in multi-threaded programming tools is studied in regards to interface issues. That's why we focus on interface. The effective adoption of a new interface is related to how inline the design decisions are with the design decisions native to the interface. Here's an example of how the proposed interface looks like. We are adding a new clause called transaction, and it allows the definition of semantics of data sharing. We can see the notation pragma OMP, a list of directives, or clause transactions with a list of options that will modify the transactions, and the other clauses. The transaction clause allows TM to be integrated into the way parallel code is implemented in OpenMP. The construction parallel transaction, for example, creates a transactional memory in the memory hierarchy and binds the threads in the pool to the TM. In other directives, the transaction is parameterized with a list of identifiers, ID, for example. There's also a preferential access mode represented by the notation OP that will indicate how the transaction might behave with mostly reads, mostly writes, or a balance between reads and writes. Another access modifier is adopt or defer. This is related to transaction nesting when one transaction is initiated inside another transaction, and this can modify that. When using the transaction clause with different directives will result in different behaviors. For example, the sections directive, the transactions are bound by the scope of each task created in different sections. For the for directive, each chunk generated will be a transaction, and the task directive, the transactions corresponds to the code associated with the task. The transaction clause that we are adding aims to simplify parallel code, avoiding the use of critical sections or blocks like the critical directive, for example. Now for the prototyping. Our proposal exploits the vanilla TM interface, which is an intermediate language designed to allow the support of our extension on different tools or libraries. The application program is developed in OpenMP using resources available in the specification of OpenMP, and the addition of a new clause to the set of service is supported by the selected STM tools without interfering in the OpenMP operation mode. Here's an architecture of how the proposed OpenMP environment is going to work. We can see the different layers of the system where we have the operation system down here, runtime OpenMP, the directive and clauses native to OpenMP, the OpenMP support library, and here we have the transaction clause with vanilla TM and STM support. Some other alternatives to vanilla TM is DynaSTM or GCC TM or other tools. Here we have a process of how to obtain the code using this proposal. We have first the OpenMP application with the transaction clause. Then there is a step of translation for the STM support that will result in a OpenMP program with calls to the STM support service. And after that is the compilation process. So this translation is a very important step. The source code. We did an analysis of source code to compare to related works, and the metric used to measure differences is the goal question metric. This metric assumes that some properties of the project can be measured, and the set of problems analyzed was the cohesion, which is a suite of toy applications used to assess the usability of parallel programming systems. The data provided by these measures can help many administrative decisions, such as selecting a programming tool. 5 questions were elected, and the goal is to characterize the use of different interfaces for TM in OpenMP. Here we have 3 of the 5 questions. The other 2 are actually just a ratio between these 3. The first one is, what is the size of the source code, where we could measure how much the addition of transactional memory support could simplify the code. The second one is how many resources of OpenMP API are used. This is just simple calls of these resources. And the third one is how many parallelization directives are used. So these are all quantified and were compared to some of the related works. Here's how it looks on the code itself. We have the original and the proposed interface. In red are the pieces that are going to be changed or removed, and the blue are how it looks in our interface. So the analyzed source codes were the OpenMP implementation of the cohesion problems, those same problems with transaction clause, and also the Nebelung and Wong implementations, which were the related works that we compared to. We also analyzed some of the GCC TM implementations and TinySTM, and the overall results were that using transactional memory in these problems, there were a significant reduction in number of code lines. There were fewer parallelization directive calls, and sometimes less OpenMP resources were used. Now for the experimentation and performance. The experiments were carried out considering 2 sets of programs. The first set is the same cohesion benchmark applications that we did analyze the source code. And the second set is a stamp benchmark called bias, and a program developed as a benchmark for pure OpenMP called K-means. 2 NUMA platforms were used, Hydra and Tekoha. Here's their specification. The performance index collected is the execution time in seconds, with an average of the last 30 executions. The samples of each case that did not adhere to a normal distribution were highlighted. And when samples did adhere to a normal curve, student's T was used, otherwise man witness U test was used. The results obtained reflect a combination of versions of the program to be compared. These versions have different execution support, different architectures, and different numbers of threads in OpenMP runtime. The step one is the prototype validation using these 6 cohesion problems, which were the only ones with TM applicability. 3 implementations were evaluated. One with a prototype of our interface using vanilla TM, one with TinySTM, and one with GCC TM. 3 input sizes according to the nature of the application, which are small, medium, or large, and execution times collected for 2, 4, 8, 16, 32, and 64 threads. Here we can see the highlighted results are the ones that did not adhere to a normal curve, and the overall analysis shows that the original OpenMP naturally produces better performances by using lower level resources. The step 2 is prototype behavior. 2 programs originally developed for performance analysis were implemented with the proposed interface. The objective is to position the proposed solution in the applicability of problems in the context of TM programming and pure OpenMP. The 2 programs are the base from the STEM benchmark and the k-means from a pure OpenMP benchmark using atomic operations. Here we have the results of these 2 programs. The k-means and base are the original program's executions, and the ones named van are the ones we adapted with our interface of transactional memory. We can see that the overall results of the addition of a TM interface show a much higher execution time, but we can highlight the base program with a small and large setup because these 2 actually showed a much better execution time than the original implementations. Finally, the conclusions and final remarks. The main results were the incorporation of TM mechanisms in OpenMP and its validation. This was carried out with the support of a prototype developed on tools offering support to TM. We explored the vanilla TM interface with alternatives such as TinySTM and GCC TM. And we concluded that the addition of a TM interface does not interfere with the OpenMP operation mode. The data resulted from source code analysis showed that the use of transactions provided fewer lines and invocations of directives compared to the original OpenMP and related works. In the experimentation and performance analysis, it was possible to verify that the prototype was operational with both TinySTM and GCC-TM, although comparisons regarding the performance did not show advantages compared to the pure OpenMP. That is all. Thank you.